Have you ever heard of a programming puzzle that's so common it actually has its own name? Well, today we're going to dive into the infamous diamond problem and explore C-Sharp's brilliantly elegant solution that manages to avoid it completely. Let's get right into it.
So here's a fundamental question in object-oriented programming. Why is it that a class can only have one parent? In C#, you just can't inherit from 2 or 3 different classes. Now, that might seem like a weird limitation at first, but trust me, there's a very specific and a very good reason for it.
And to really get that reason, we need a quick refresher on inheritance. It's basically this core idea that lets you create a new class, say a sports car, that automatically gets all the features of an existing class, like a car. It's a super powerful way to reuse code and build really logical connections.
Okay, so this brings us to a really crucial design choice. C# specifically enforces what's called single inheritance, which just means a class can only get its DNA, so to speak, from one parent. Some other languages out there do allow for multiple inheritance, where a class can have a bunch of parents. But C# intentionally avoids this to prevent one very specific and, frankly, very confusing problem.
And that problem is the star of our show today, the infamous diamond problem. It's a classic inheritance puzzle that perfectly shows why having multiple parent classes can get messy and get messy fast.
So, what exactly is this problem? Well, it happens when a class at the very bottom tries to inherit from 2 parent classes. But here's the kicker. Both of those parents inherit from the exact same grandparent. You see how this creates a kind of diamond shape in the family tree? Yeah, and it leads to a total logical dead end. All right, let's actually build this thing out step by step so you can see exactly what happens. Imagine we start with a single ancestor. We'll call it class A. This is our grandparent class, and it has one method, a basic action that we'll just call do something. Simple enough, right?
Okay. Next up, 2 new classes, B and C, both inherit from A. These are our 2 parents. But here's the twist. Each parent decides to create its own special version of that do something method. So now we've got 3 conflicting versions of the same function floating around in our family tree.
And here it is. This is the moment the whole thing just blows up. A new class, D, comes along and wants to inherit from both B and C. It wants to get all the good stuff from both parents, but the compiler just hits a wall. When class D tries to call do something, which version is it supposed to use? The one from parent B or the one from parent C? There's no way to know. It's completely ambiguous. This is the diamond problem. And it's the exact reason C# just says, nope, not going to do it. So if C# just flat out blocks this kind of inheritance, how do you get the functionality you need from multiple places? Well, the answer is C#'s really elegant solution, interfaces. The idea is, instead of inheriting the actual code, you inherit a blueprint.
You know, this solution gets right back to the core philosophy of C#. The language was designed from the ground up to prioritize simplicity and clarity. It intentionally avoids messy situations like the diamond problem, just to keep our code readable and easier to maintain in the long run.
So, what in the world is an interface? Well, think of it like a contract or a blueprint. It lists all the methods a class must have, but, and this is the most important part, it provides 0 code for how those methods work. It defines what a class must be able to do, but leaves the how completely up to the class that actually uses it. I know this might sound a little abstract, so let's make it way more concrete with a fun example that really shows how powerful interfaces are. Let's build ourselves a flying car. Okay, so here's our game plan. First, we create two separate blueprints. An iDrivable interface that says anything that uses me must have a start method, and an iFlyable interface that says you gotta have a takeoff method. Next, we build the individual parts. We'll have a car class for the driving and an airplane class for the flying. And finally, we assemble it all. Our new flying car class simply promises to follow the rules of both of those blueprints. And the result? Well, our flying car now has the best of both worlds. It can start its engine just like a car, and it can take off just like an airplane. It has effectively gotten behaviors from two totally different concepts, but without any of the ambiguity or conflict that we saw with the diamond problem. It's just a clean, safe way to get to the same goal.
And hey, this isn't just for sci-fi vehicles. This pattern is used absolutely everywhere in modern software. So let's look at another quick real-world example: electronic devices. This whole approach just gives you incredible flexibility. Imagine defining interfaces like iConnectable and iBattery powered. As you can see here, both a smartphone and a laptop can promise to fulfill these contracts. They share some common abilities, but each device gets to implement them in its own unique way. So, let's start to wrap this up by looking at why this approach is so much more than just a clever trick. It's actually a cornerstone of good software design. Why does this all matter for us as developers? Well, using interfaces gives us some massive benefits. First off, obviously, it completely sidesteps the diamond problem. But it also naturally pushes you to write cleaner, more modular code. You end up building systems almost like you're snapping together Lego bricks of functionality, which is absolutely crucial when you're trying to build complex software that you can actually maintain over time. You know, this quote really says it all. By embracing this interface-based design, we can create really flexible, modular code to solve complex problems. And we can do it all without sacrificing that simplicity and clarity that makes for truly great software.
So, we've seen how C# uses interfaces to neatly sidestep a major programming puzzle, letting us create these complex designs while keeping everything simple and clear. And that leaves us with one final question to chew on. If interfaces are this powerful for combining different behaviors, when is good old-fashioned single-class inheritance still the right tool for the job? That's a great topic for another time. Thanks for watching.